Can everyone hear me? Awesome. Okay. My name is Jade. I'm going to be talking about the secret sauce of vendor-neutral GPU programming, specifically about Chapel. I'm an engineer at HPE working on Chapel, so I care a lot about it. So why should you care? If you've ever written CUDA code or HIP code, you know how painful it can be, especially compared to a Python programmer who is used to just writing easy Python code, and now you're writing CUDA code, and you're locked into an NVIDIA GPU. So what do you need to kind of escape that? So I say, what is the secret sauce? And I'm going to say there's a few things that you really need. This is my opinion. What do you need for a programming language to not only provide performant GPU code, but portable GPU code? So not just for NVIDIA, but also for AMD and anybody else who might have GPU accelerators, what have you. You need a modern programming language. It can't just be another library for C or C++. It can't be another library on put your favorite programming language here. It needs to be a first-class citizen. You also need, that rest of that support for that programming language, your compiler that can target multiple GPU vendors, and a runtime which allows you to extend to all those other GPU vendors. Does something exist today? Yes, of course. It's Chapel. So if you haven't heard of Chapel before, Chapel is a modern parallel programming language that's designed to be portable and scalable. And of course, it's open source, as all good software should be. The idea of Chapel is if you have a parallel computing resource like a CPU or a GPU, you should be able to write Chapel code to drive that hardware. So we want to support general parallel programming, not only with CPUs, GPUs, your accelerator here, and we want it to be easy to do. So I mentioned Python programmers. We want anybody to be able to pick up the programming language and start writing it and not have to worry about weird templating things in C++ or their memory management and stuff like that. So to describe this first-class parallel programming experience, I'm going to show it by example, because I think that's the easiest way to read through this code. So on the left side of the screen here is our little model of what a computer might look like. I've called my computer a locale. That is a Chapel term. And I have some CPUs associated with it. And those CPUs have some memory that are attached to them. And I might have one or more GPUs associated with it. So here I have 2 GPUs. And I'm going to run some code through this computer and do something with it. So the first thing I'll do is declare a CPU array. And I'm just writing my array at global scope of the program. And as long as that variable is there, I can access it, and I can access the CPU memory. I'm then going to declare some GPU arrays, and I have a slightly different syntax. So I'm literally saying on this computer, in this specific GPU, in this locale, I want to declare 2 different arrays. One is B, one is C, and I'm putting them on 2 different GPUs. Now, the syntax makes it look like these aren't at global scope, just because of the line spacing. These are also at global scope. I can access them from anywhere in the program that they're in scope. And now we get to do actual computation. I have this magical parallel for all loop where I can tell the compiler, this is my order independent loop, and you should parallelize it in the way that you can. So for example, I'm running at this global scope. So therefore, I'm running on my locale 0, and I'm going to use all of my available CPUs to do computation. Now, I can take this exact same loop, and I can put it inside of this on statement, and I can say, now tell the compiler, you have the same order independent loop, and I want to put it somewhere else. And so here I'm saying, put it on this GPU. And so this one extra line of code allows me to launch a kernel on a single GPU. And for those of you who have written, low-level GPU code, I hope that that simple little for all looks a lot nicer than maybe CUDA code does. And lastly, this is a productive parallel programming language. We don't want to always be writing these large loops. Maybe we want to be more concise. And so we have the bottom version, which is pretty much the same thing as the for all loop, but now we're expressing it in a very productive form, and maybe something more natural to a Python programmer or someone who's not as familiar with programming. All right. So using kind of those constructs, we can compute across all of those GPUs. So I'll run through this example here. I'm going to go through all of the GPUs that are available to me and do a computation on each of them in turn. So we'll execute them on them in serial. There's GPU 0, followed by GPU 1. This is a parallel programming language. Let's do them at the same time. So let's execute on them all in parallel. I'll save you kind of a diff of these two. All that is different is I've changed the keyword. So instead of saying do this in serial, I'm saying do this in parallel. And I get GPU. Now, this is our high-level parallel programming language. How do we actually make this work? The secret really is leveraging open source software. LLVM drives much of our code generation. So we take our original high-level Chapel code, and we're going to do a lot of transformations on it to get it ready for LLVM and GPU-based compilation. So the actual order-independent loop for a GPU, we need to turn it into something that is ready to be turned into a kernel and launched across the GPU. And for the CPU, we will just turn it into something similar to a parallel loop like OpenMP or whatever your favorite parallel library is. These then happen at the same time, and then we'll split them apart into two different invocations of LLVM, one to target whatever we might care for the GPU, and then normal CPU compilation. And all of this then gets packaged together into your final executable to launch your Chapel code. And we can kind of plug in your favorite accelerator here into this LLVM engine, leveraging that open source software. And the last piece of the puzzle here is having an extensible runtime architecture. So this is Chapel's runtime architecture, which is also open source. And you have a very common part of the code, which is this GPU layer. And then you can split out the very specific portions that go for the CUDA API versus the AMD HIP ROCm API, and split it out. Chapel also supports this CPU interface, which allows you to pretend like you have a GPU even when you don't, which is really great when you're running on maybe a laptop that doesn't have the same resources as your actual compute server. And as a bonus here, Chapel is designed to be parallel. So of course, we want to use many, many computers. So now, not only do I have locale 0, but I have locale 1. And I can launch my computation across all of these nodes using all of the GPUs with a very succinct piece of code. I can go across all of the compute nodes and get distributed computation. So this has been a very lightning fast overview of Chapel's GPU support. There is so much more to it. If you want a much deeper dive into Chapel's GPU support, more of that nuts and bolts that I gave the high-level overview of, that top video is a great resource. Chapel's kind of internals of the runtime in general is that middle one. And if you don't care about the internals and you just want to write GPU code, that bottom one is a part of a series in writing GPU code in general. So I mentioned Chapel is an open source community. There's lots and lots of ways to connect with us. I will highlight the Chapel project meeting, which was very recently made public. So if you are interested in Chapel, especially Chapel with GPUs, designing a language, come meet with us. We are happy for people to collaborate with. That has been a lightning fast talk on GPUs. Thank you all very much. Yes. So in MATLAB, you get a performance penalty for writing the loop. So the way that that's dealt with in Chapel is, and I'll actually go back to that. So that this bottom version here turns into that top version. So they ultimately are the same code that's being run. So there's no, there can be penalties for writing sometimes the nicer version, but they ultimately result in the same thing. So you should get the same no matter what. Yes. So this is a feature called promotion. And promotion, like a very long expression like that, gets knitted into a single loop rather than separate loops one at a time. Yes. So, I mean, so part of Chapel's original goal was distributed computing, targeting something like InfiniBand, which we do run on. And so Chapel, and I'll go back to the runtime. So way over here is Chapel's communication layer, and we have those same kind of primitives for just general communication across the network between the CPUs. And Chapel's GPU support is much newer, and so there's active work being done to more tightly integrate the GPU layer with that communication, especially related to that last work. Yes. So yes, the kind of simplest way to think about it is if a variable is in scope in like the programming language, you should be able to access it and compute with it. So, right, I've declared array B inside of this GPU, but if I then nested another call to a GPU, I could copy from one GPU to the other. Thank you.